The topic for today is what I'm going to call exact recovery in cut problems. So let me tell you what I mean by exact recovery. This is a topic I actually surreptitiously already introduced you to on Monday. So in exact recovery, the question you're trying to understand is, for a given algorithm that you have in mind, figure out which inputs this algorithm works properly on. So solves the problem correctly. Okay? So for what inputs does a given algorithm A solve the problem exactly? Our main theorem on Monday was exactly this type of exact recovery guarantee. We proved that single link plus plus exactly recovers optimal solutions in 3 stable k-median instances. Okay? That was the main theorem on Monday. So I really want to sort of tease out, that kind of property and give you some more examples of these kinds of exact recovery results. Now, okay, so what's the motivation for these kinds of guarantees? So, here we're thinking of this algorithm A as something which either we already have access to, right? So maybe like today it's going to be linear programming. Okay, so Stanford has a site license for Cplex, so this is an algorithm we can just run, okay, for free. We just feed in input, see how it does. Or it's an algorithm which would be very easy to code up. Okay, so a simple algorithm like single link plus plus. All right. So, and the idea is, and this is really often the case in practice, where designing an algorithm from scratch, especially a complicated algorithm, was sort of a last resort. Right? Really, it's much preferable that something in your existing toolbox suffices for the problem at hand, at least for the inputs that you care about. That's actually how most clients of algorithms actually use them. By contrast, not all, but a majority of theoretical research on algorithms kind of says, let's try to come up with new algorithms, which is a lot of fun and really interesting, come up with new algorithmic ideas, often general purpose. But here we're really going to sort of take this different approach. We have our algorithms that we're allowed to use in hand. Let's understand what kinds of inputs they work on. All right. So the theory I'm going to be that we talked about Monday, today, and then at least one lecture next week, all is trying to capture sort of that use case, if you will, formally, with formal theory. Okay. Good. So we're going to do another case study today of exact recovery, and it's going to be graph cut problems. Okay, which are quite similar in spirit to clustering problems. Okay, you're taking a graph and breaking it into pieces. The difference is going to be on the kind of algorithm that we talk about. Namely, I really want to talk about just linear programming. Okay, so when does linear programming exactly recover solutions to NP-hard graph cut problems? Right? So that's the topic today. So when our NP-hard problems solved exactly by a linear program. Okay? So the answer, of course, is not going to be always, because if you don't know this already, I'll tell you right now, linear programming can be solved in polynomial time. So if we're talking about an NP-hard problem, we're not going to solve worst-case instances of linear programming. But maybe we can solve a lot of instances that we care about. All right, we want theory to explain when it works well. So the segue that I'm sort of doing today is I'm keeping the kind of conclusions that we're going to be proving similar to last lecture. Okay, so we're still going to be doing exact recovery for clustering style problems, but I'm sort of shifting the algorithm on you. I really want to start talking about linear programming, because it turns out a lot of the sort of greatest hits in exact recovery are for proving relaxations, linear programming, or convex programs, proving them exact. Okay, so I want to push us toward the direction of understanding linear programs. So that'll allow me to next week hopefully say a little bit about some hot topics like compressed sensing and stuff like that. Okay. All right. So similar guarantees, but with linear programming algorithms. So the first part of the lecture, I just want to give you a relatively gentle introduction to how this is going to work. Okay. So I'm going to talk for maybe the first half of the lecture or so about a problem some of you, I'm sure, have seen, the ST min cut problem. Okay, so the dual problem to max flows. All right. So this problem is actually solvable in polynomial time. So it's not really the type of problem where you are going to ask a question like this. But later on in this lecture, we'll look at an NP-hard generalization of min cut, and then we'll extend the same techniques to get the exact recovery results that we want. Okay. All right, so for those of you that haven't seen ST-min cut or need a reminder, so the input here is an undirected graph with costs on the edges. Okay, sometimes they're called capacities in this context. I'm going to go with costs. Okay, so positive costs on the edges, and there's a source vertex, and there's a sink vertex. And the problem you're trying to solve is you're trying to identify the minimum ST cut. So the ST cut, which cuts the minimum total cost of edges. Okay? So this is something you definitely spend some quality time with in CS261, for example, for those of you that have taken that class. Okay, so first of all, remember what a cut is. A cut is just you take the vertex set and you partition it into two groups, A and B. What makes a cut an ST cut? S, this distinguished source vertex, should be on one side. T, the sink vertex, on the other side. Okay, so little s is in capital A, little t is in capital B. That's an ST cut. And among all ST cuts, we want to minimize the total cost of the cut edges. Where, of course, a cut edge is just one with one endpoint in each of the two sides, one in A and one in B. Okay? So, for example, a picture you might want to have in your mind would be a graph like this. So here's S, here's T. So those are the edge costs. So stare at that graph for a second and try to figure out what the value of the best ST cut is, the minimum ST cut. What do you think? Heard a 7, heard a 6. I think it's 6. So if that's A and that's B, that separates S from T and it cuts 6 edges. And I don't think there's any cheaper one. Yeah? Okay. So if you want, you can solve the minimum cut problem using lots of pretty maximum flow algorithms, which you study in CS261. That's not what I'm going to do here. Rather, I'm going to show you how we can just solve a linear program, and the integer solution, the optimal solution, is just going to pop out, okay, as the exact answer to this linear program. All right. And then we're going to generalize it shortly to NP-hard generalizations of this cut problem. Okay. So I'm going to assume. So we're given an input like this. I'm not going to assume any stability condition, anything like that. I don't need to. I will assume that the optimal solution is unique. Okay. So that's like a super, super weak version of stability. Okay? Only one optimal solution. All right? It's not really that important, but it'll just make things simpler. All right? Now, so actually, let me ask. So how many of you, who really knows nothing about linear programming or feels like they know nothing about linear programming? Okay, a couple of you. That's fine. Good. We won't need too much. So what I'm going to do next is show you a linear program which is meant to capture this minimum cut optimization problem. Okay? So just the cartoon, I talked a tiny bit about linear programming in lecture number 1. And so remember, there's this cartoon. The upshot is you want to maximize a linear function over linear constraints. So you have a feasible region, which is the intersection of half spaces. So it just looks like a polygon in 2 dimensions. And then you have some linear objective function. That just means you want to push in some direction as far as possible. And so linear programming is just meant to find the point in the feasible space, which is as far as possible in the desired direction. Okay, so that's the sort of geometric picture you should have in mind. Now, so the way you specify a linear program is first you got to say what your variables are, your decision variables. Okay. Then you got to say what your objective function is, which should be linear in the variables, and you got to say what your constraints are, which should also be linear in the variables. So let me show you such a linear program meant to capture minimum cut, or at least a relaxation of minimum cut. Okay? So the variables, so there's going to be a variable xe per edge. And the semantics of xe is that we want xe to be 1 if this edge winds up getting cut, and 0 if this edge is not cut. Okay, that's the intended semantics. We're also going to have a vertex for, a variable for each vertex. So here the semantics are, if dv is 0, that means we're thinking of v as being on the source side, the s side of the cut. If dv is 1, then it's on the sink side of the cut. Okay, so those are the two variables, two sets of variables. All right, so what are the constraints? Well, certainly s better be on the s side of the cut. Okay, so we fixed ds at 0, that's tethered there. Similarly, t better be on the sink side of the cut, so that's tethered at 1. Okay, the other d values are allowed to range freely. And then we want to say something that we want a constraint, which says that if u and v are on different sides of the cut, okay, if the vertices u and v are on different sides of the cut, and there happens to be an edge between them, well then that edge gets cut. Okay, so I'll show you the constraints that indicate that. So for all edges with endpoints u and v, we have a pair of constraints which says xe is at least du minus dv, that's an xe, and xe is also at least dv minus du. Okay? So this is just saying, xe is at least the absolute value of the difference between du and dv. Okay, I wrote it this way so it's obviously linear in the decision variables. Okay. The point here is that if one of the d's is 0 and the other is 1, this forces the x to be 1. Okay, so if the nodes are on different sides of the cut, it forces the edge to be cut, which is what we want. Okay? All right. And then with the decision variables, I hope it's kind of quite clear what the objective function is going to be. So xe just is supposed to denote whether the edge gets cut or not. The objective function, of course, is to minimize the total cost of the cut edges. So the objective just sums over all of the edges. It looks at whether or not that edge got cut, and if it does get cut, if this is a 1, then you pick up its cost CE. Okay? And you want to minimize this. All right? So that's a linear program whose intent is to capture the minimum cut problem. And it's at least a partial success in the sense that if you show me an ST cut, that certainly naturally induces a feasible solution to the linear program. You show me the cut that sets A and B. I'll set all of the D's equal to 0 for vertices in A. I'll set the D's equal to 1 for the vertices in B. And I'll set X's to be 0 or 1 depending on whether the edge is cut, is not cut, or cut, respectively. Okay? Really, by definition we've basically engineered this linear program so that cuts would give you feasible solutions. But now remember, the feasible solutions to a linear program, they're not just a bunch of discrete 0-1 points out in space. Feasible regions of linear programs look like this. They look like convex sets. Okay? So they include other stuff than just the things that we had in mind, than just the sort of the 0-1 vectors for cuts. They have, in particular, fractional solutions. Okay? And so a linear program, you optimize over the entire set of feasible solutions, the fractional ones and the integer ones, the ones we care about and the ones we don't care about, and you get whatever you get. You get whatever's optimal. Okay? So the concern always with when you try to formulate discrete problems, like a cut problem, as a linear program, is that when you solve the linear program and you get the optimal solution, it's not meaningful. Okay? It doesn't actually correspond to a discrete solution. It corresponds to some fractional thing that you can't interpret. Yeah?
I mean, we know for linear programs that there's one optimal solution that is, I don't know what the correct term is, but basically an extreme solution. So
okay.
It would be right.
And therefore, there's no guarantee that that's not fractional either in general. Okay.
In general, no.
In general, no.
But here,
yeah. Well,
maybe.
Here I wouldn't expect you to necessarily know anything, but I'm going to prove something about it. Okay?
Yeah.
So in general, when you formulate linear programming, you intend for them to be formulations, but frankly, they're relaxations. Okay? They include stuff beyond the just integer solutions you're trying to capture. And so when you optimize over the linear program, you might conceivably get a fractional solution, which is not what you want, which really just doesn't correspond to a feasible solution of your original optimization problem. Okay? However, okay, well, first of all, so facts. And again, this is something you just, even if you don't know why this is true, all of you should know this is true and remember forever that this is true. So fact, linear programs can be solved efficiently. Okay, that's true both in the practical sense with the appropriate commercial software, and it's also true in the theoretical sense in the sense of polynomial time solvability. Okay, so you should know both of those things. So can solve LP in poly time. Okay? It's not essential that you know why. Okay? And in fact, frankly, most people who use linear programming, both in practice and in theory, treat it as a black box, okay, and don't know a lot about the why. Okay? So if you're feeling very keen, by all means learn more about it. Okay? There are people who are experts in this, and it's useful skills, but a lot of people just use linear programming without actually understanding it. And that's a totally acceptable and normal thing to do. And that's what we're going to do in this class, needless to say. Okay? There's some other great classes at Stanford where you can peek under the hood and see how these things actually work. And those are fun as well. Okay, but so here's the claim. So the claim is that the optimal solution to this linear program is not something that we can't interpret. It's not fractional. In fact, is integral. Okay? So we just write down this LP, we just stick it into our favorite LP solver, and out pops on a silver platter this unique optimal cut. Okay? So we just run this algorithm, which presumably someone has coded up and engineered very well, and it just gives us exactly what we want. Okay, so that's a pretty sweet guarantee, actually, right? Okay. So any questions before I start explaining why this is true? This isn't obvious. And the proof is not that long, but it's not an obvious statement. Right, I meant to say, just to illustrate sort of like what fractional solutions might look like, on that graph over there, imagine in this graph, you set all of the x sub e's equal to a fifth in this graph here. Okay? So you could, for example, set d here to be a fifth, d here to be 2/5, the d value here to be 3/5, and the d value here to be 4/5. And you could set all of the x sub e's equal to 1/5. Okay? That would be an example that satisfies all of these inequalities. Okay? And it does not, it doesn't correspond in some obvious way to a cut. Okay? If it feels like kind of a superposition of a few cuts, that's good intuition. It is. Okay? But it's not obviously a cut, okay, to have all these fractions. Okay. So the proof of this claim is pretty neat, actually. I mean, there's a bunch of ways to prove it. But this has always been one of my favorite ways to prove it, the way I'm going to show you now. And then it's also going to generalize nicely to NP-hard generalizations, okay, as a bonus. All right, so let's have some notation. So C star is going to denote the optimal min cut. Okay, so this is the optimal integral solution. Okay, so this is really a partition into A and B. And F star is going to be the edges that are cut by C star. Okay, so there's a partition into A and B. These are the edges of one endpoint on either side. All right? So some notation. So now for an arbitrary ST cut C, so some other partition into A and B, I'm going to define delta of C. Okay? Now C star is the min cut, it's the cheapest. Okay? So every other cut is at least as expensive. Delta of C is just a formula for how much more expensive C is than C star. Okay? And it's some kind of symmetric difference formula. Okay? So why is C more expensive than C star? Well, presumably, there are some edges that are not an F star, meaning the optimal cut doesn't cut these edges, but C does. Okay? So this is the extra cost in some sense that C is getting hit by, which C star is not. Now, on the other hand, we got to give this cut C a rebate for any edges which the optimal cut C star is cutting and C is not. Okay, so we subtract off an analogous term. If the optimal cut does cut E and C does not, then we have the corresponding rebate. Okay? So this is just the amount by which C's cost exceeds C star's cost. Okay? So a very simple observation, just because C star is the unique optimal cut. So obviously delta of C star is 0. Both of these sums are vacuous. And any other cut, this is going to be strictly positive, right? Because we assume C star is the unique optimal cut. Okay? But that's really just some notation. Okay? Delta. How much worse other cuts are than C star. Okay. So now I want to do the same thing with respect to the optimal LP solution. So this was all about cuts. Okay? There's no linear program over here. This is just about cuts and graphs. All right? Now let's think about feasible solutions to the linear program, which, as we saw, can have fractions. Okay, the x's are in general fractions between 0 and 1. All right? And I want to write down sort of this same delta. Okay? But let me just point something out. Okay? So if we're talking about the optimal fractional solution, the optimal linear programming solution, now all of a sudden the optimal fractional solution is only going to be better, only going to be cheaper than C star. We agreed that every cut induces a feasible solution to this linear program. Okay, so every cut, in particular C star, is one of the feasible points, and this linear program is optimizing over all points, including in particular the one representing C star. So it can only be better, it can only be cheaper. Okay? So now I'm going to write down another delta term, but it's actually going to be non-positive, right? Because the optimal fractional solution can only be better than the optimal integer solution. Okay? So similarly, so suppose we solve this to optimality. So we got our x hats and d hats. That's what makes this as small as possible over the whole feasible region. That's a d hat. So opt LP solution. And so now we define delta of x hat in exactly the same way. Okay, so it's the extent to which x hat is more expensive, even though we know it's actually cheaper, so this is going to be non-positive, more expensive than the integral solution C star. Okay, so we have these two analogous sums. So we say, well, first of all, if there's anything that the optimal solution doesn't cut, so it incurs 0 cost on this edge E, meanwhile, our fractional solution x hat incurs some fractional cost, right? It contributes the corresponding term to its objective function. Okay? So these are edges on which the optimal min cut C star incurs 0, and we incur whatever we incur, according to x hat. Now the other term, we say we also get this rebate, though. So for any edge which which C star cuts, that corresponds to sort of an x value of 1, to the extent that our x value is less than 1, we get that difference back as a rebate. Okay? So again, it's C sub E. 1 is basically what the C star is paying. So the extent to which x hat is less than 1, that's a bonus that we get. That's a rebate. Okay? So that's just exactly the same computation with a fractional solution instead of with these cuts, these integer solutions. And we already discussed why it must be the delta of x hat is at most 0. Okay? C star is one feasible solution. X hat is the optimal feasible solution. It can only be better. So delta can only be non-positive. Okay? So that's going to be, that's 2. All right. So that's kind of the boring stuff, relatively. Here's what's pretty cool. All right? So how am I going to, remember what we're trying to prove. Okay? We're trying to prove that actually the optimal solution is going to be integral. All right? And it's going to be an algorithmic proof. Okay? So I claim that there exists a randomized algorithm that takes as input x hat. Okay, so it takes in this possibly fractional solution x hat. And then it's going to output an ST cut, a random ST cut. It's a randomized algorithm. Okay? And here's the property that that distribution over ST cuts is going to have. Okay, so C here is a random variable. It's a randomized algorithm. Okay. Such that for all edges, all right, so again, for a given edge, because the cut is random, sometimes the edge will get cut and sometimes it won't. Depends on what exact cut capital C this algorithm spits out. But the fraction of the time, the probability that C cuts E is going to be exactly the LP solution value, x hat E. Okay? So these x hats are between 0 and 1, right? That's sort of like the fractional extent to which the edge is cut in this LP solution. And I claim that I can exhibit a randomized algorithm. I have to show you what it is, obviously, but I claim I can exhibit a randomized algorithm so that the distribution of the cut satisfies the property that the probability a given edge is cut is exactly the fractional cut value, if you like, in the LP, exactly x hat E. And of course, that means, in addition, obviously, the probability of the complementary event that E is not cut, that's going to be just 1 minus the probability that it is cut. So the probability it's not cut is just 1 minus x hat E. Okay? So that follows immediately from the first statement. So let me show you why, assuming the lemma, we're done. Okay, I want to show you that the lemma implies the claim. Then I'll show you the algorithm which proves the lemma. Okay? And the reason I'm emphasizing this argument, the part of the argument which is going from the lemma to the claim, this argument we're going to copy almost identically in the more general setting. Okay, so the algorithm itself will have to change, non-trivially. So the proof of the lemma will look quite a bit different depending on the problem, but this argument I'm about to show you will just sort of extend very easily. Okay, so this is the argument which you should be ready to see a second time later in the lecture. So proof that the lemma implies the theorem. So suppose we actually constructed an algorithm with this property. So here's the intuition. Okay, so we're trying to prove that the fractional solution has to be this unique, this unique min cut. All right. So we have two things working in different directions. Okay, we have one which says every integer cut has positive delta. Okay, except for C star where it's 0. But then we also have this fractional solution where the delta is non-positive. Okay, so in some sense here the fractional solution is better than C star. So if we have a distribution which matches the linear program, okay, that means basically this randomized algorithm is averaging over a bunch of ST cuts, a bunch of integer solutions C. Okay, it's a randomized algorithm, it spits out a cut, that means it's a distribution over cuts, integer cuts. We know that every single integer cut is only worse than the optimal one, strictly worse unless it's actually C star. Okay? On the other hand, this lemma kind of says that our distribution, our randomized algorithm, is doing an exact simulation of our linear programming solution, and the linear programming solution is at least as good as the integer solution. Okay? So that basically saying that this distribution has to be a point mass of probability 1 on the unique optimal cut. Okay? Anything else would give us a contradiction. So that's sort of the very high level idea. And the proof really just formalizes those couple sentences. All right? All right, so let's look at so we have this distribution over cuts, this randomized algorithm that spits out a cut. Let's calculate, on average, how much worse this cut is going to be than the optimal one C star. Okay? We know it's either going to be C star or it's going to be something strictly worse. We know that. Well, so here's delta of C. Okay? So by linearity of expectations, the expected value, okay, remember what's random. Okay, C is what's random, the cut C. So by linearity of expectations, this is very simple to calculate, this expectation. Okay, we can just do it term by term. So we have a sum over the edges that C star does not cut of the contribution, if we cut it, times the probability that we, meaning our randomized algorithm, cuts it. Okay? So C cuts E. All right? So that's just looking at the probability that that predicate is actually met. Same thing here. For the second term, we say, okay, well, what about the edges that were cut by C star? Whenever we don't cut it, we get the rebate. So we want to know what's the probability that our randomized algorithm spits out a cut which does not cut E. Okay? So that's just linearity of expectations applied to this equation. Now the lemma tells us that our randomized algorithm cuts an edge with probability exactly equal to the linear programming value. Okay? So this is x hat E by the lemma. Okay? Similarly, it says the probability that we don't cut an edge is exactly 1 minus the linear programming value for that edge E. Okay? So again by the lemma, this is 1 minus x hat E. Okay? But having done that substitution, we now see that expression is exactly what? Still on the board.
Objective of the LP, or the delta.
Delta of x hat. Okay? What we have on that middle part of the board is exactly delta of x hat. Okay? Which we observed is non-positive. Right? Because the fractional solution is at least as good as the optimal, best optimal solution. Okay? So all of this is in most 0. And this is by 2. Okay? All right, so let's remember, so what have we done? The dust is settled. This says the randomized algorithm spits out a cut which on average is at least as good as the best cut. Okay? The randomized algorithm spits out a cut that on average is at least as good as the best cut. How could that possibly be true? Okay? There's one best cut, everything else is strictly worse. Okay, so if you give me a distribution over cuts, which is as good as the best cut, it has to be outputting the best cut with probability 1. Okay? Any probability on any other strictly worse cut would make the average strictly worse. Okay? So, it outputs C star with probability 1. All right? Now, this isn't quite what I claimed. I claimed that the LP solution you started with has to be integral. Once I show you this randomized algorithm, it'll be obvious that the only way the randomized algorithm would ever deterministically always do the same thing is if you feed it an integer solution. Okay? So I'll leave that for you to think about outside. Okay? So the fact that this randomized algorithm is actually deterministic means that x hat has to be integral. Okay? So any questions about that? Yeah.
And so this deterministic part is probably coming from the fact that we're assuming that the optimum is unique in some sense?
Yeah, I mean, so the theorem I'm proving is still true anyways. So I'm actually proving a stronger statement here, which is that the only optimal LP solution is integral. So if you have multiple optimal integral solutions, then by convexity, convex combinations of them are also optimal for the linear program, and those are fractional solutions. So in general, what's true about min cuts is that basically you've got a bunch of vertices corresponding to the minimum cuts, and then any other convex combinations are also minimum, optimal for the LP, and that's it. So there's some face of the cut polytope which is optimal. Sure. All right, so I owe you the algorithm. So proof of lemma, or proof sketch of lemma. So what is this magical randomized algorithm that outputs, it always outputs an ST cut, and the probability it cuts a given edge is exactly what the LP says it should be. Here's what it is. Okay, so remember what a linear programming solution looks like. Every vertex has a D value. okay, that's between 0 and 1. And 0 means you're on the source side, 1 means you're on the sink side. For a general solution, it might be somewhere in between. And then you have these x hats, which is the extent to which the edge was cut. Okay? So here's what the algorithm does. You start at S and you blow up a balloon, okay, to a random radius between 0 and 1. And the S side of the cut is just whatever is captured in your balloon. And the sink side is whatever else there is. That's the whole algorithm. Okay. So pick a radius strictly between 0 and 1, uniform at random. Set the source side of the cut to be the vertices such that d hat v is at most r. Remember, the d value of s is 0, so that certainly goes into A. And also, t is at 1, and r is less than 1, so t certainly goes on the opposite side. So this is certainly an ST cut with probability 1. And I'll leave it for the homework that you check this works. All right? It's quite simple. Okay. So if you take a given edge, let's say a 0.2 is its x value, it's cut exactly 20% of the time when you pick this random radius. Okay. Also, to fulfill a previous promise, I said, the only way that the randomized algorithm is going to be deterministic is if you feed into it an integral solution. Okay? That should also, certainly if you do this easy exercise, it's also going to be clear. If it's not an integer solution, that means there's some edge which is, has a value of like 0.1. And that means there's going to be some values of r where it gets cut. Okay, there's going to be some value of r where one endpoint goes to the s side, and there's going to be some values of r where that doesn't happen. Okay, so as you vary the choices of r, you really will see distinct cuts. Okay? So if any fraction means you can have multiple different outputs from the algorithm, that means if you have a constant output of the algorithm, it has to be integral. Okay? All right. Any questions about that? All right. So this is not a new result. This kind of stuff has been known for, really 50 years probably. But let me show you how we can do a very, very similar argument and prove that for an NP hard cut problem, okay, so a harder problem, but under a more stringent assumption, so not just a unique optimal solution, but more generally a stable instance, we can again get exact recovery by just solving a linear program. Okay? So the more general problem is called multi-way cut. And it's all exactly the same, except instead of just having one source and one sink, you now have some number of terminals, and there's going to be 3 or more. Okay, so before we had 2 terminals, one we called the source, one we called the sink. Now we're going to have k terminals where k is at least 3. Everything else is exactly the same. Okay? So input, undirected graph, costs, and you have terminals t1 up to tk. Okay? And the goal is a cut, so what's called a multi-way cut. So you're going to have a partition of the vertex set now not into 2 non-empty groups, but into k non-empty groups. And now instead of just having a source side and a sink side, you have one group corresponding to each of the k terminals. Okay, so ti and si for all I. Minimizing total cost of cut edges. Okay? So now in general, you're going to have a T1, you're going to have a T2, you're going to have a T3, and you're responsible for slicing up the graph into 3 parts. There should be exactly one terminal in each of the parts. And again, an edge is cut if its endpoints are in distinct parts. You want to minimize the total cost of the cut edges. Okay?
Is this NP hard even for k equals 3?
This is NP hard even for k equals 3.
What's the intuition behind why it suddenly becomes hard?
It's not clear how you'd make it a flow problem immediately.
Yeah, well, I mean, yeah, so you sort of lose a bunch of things at once. It's hard to, it's a little, I mean, it's sort of similar to saying, you know, what's the intuition for why is 2 sat NP and 3 sat NP hard? It's kind of a hard question to answer. I mean, so certainly one thing, like one way you could convince yourself something's going on is you could play with some small examples and observe that the analog of the Max-Flow-Min-Cut theorem doesn't hold once you have 3 terminals. That's probably how I would start developing intuition about why something more complicated is going on. Yeah. Okay. Good, so this is NP hard even for k equals 3. So we're not going to just write down some linear program with no assumptions and expect it to solve to an integer solution. Okay, that's just not going to happen. Instead, we're going to write down a linear program, add a stability condition, and then we actually are just going to solve it, and the integer solution will just pop out. Okay, that's what's going to happen. All right, so harder problem, stronger condition, we get the same result. All right, so the stability condition we're going to use is the same one we studied on Monday. So it's going to be this one where we think about, we basically imagine as a thought experiment perturbing the input. Okay, so here the input being the edge costs. We're going to be allowed to blow them up by up to a factor of gamma. And we want the optimal solution to remain invariant no matter how we twiddle with the edge costs. Okay? So it's different than a week ago, but it's really exactly the same as Monday. All right? So it's again gamma stability. So opt is invariance. So here opt, I really mean, you know, the integer solution. Okay, so the minimum cost multi-way cut under perturbations of the form CE goes to sigma E, CE, where sigma E is in between 1 and gamma. Okay? So on Monday we talked about k-median instances. We had this metric. We were allowed to blow up distances by up to a gamma factor. Here it's the same thing, just on the cost of the graph, of the edges of the graph. Okay? And remember that, you know, the bigger we take gamma, the more restrictive this condition is, and the fewer instances we're talking about. So the tractability can only increase as we make gamma bigger and bigger and bigger. Okay. All right. So here's the theorem. And this is recent. This is just from earlier this year. Makarichev, and Vijaya Raghavan from the main algorithms conference, January this year. So for all gamma stable multi-way cut instances with gamma greater than 4, the LP solution, of course I haven't told you the LP, but I will tell you the LP. Okay, so there'll be an LP. And the theorem is going to be that the optimal solution to this LP is in fact the stable multi-way cut instance. So it does solve to an integer solution. Okay? So that's what I want to prove for the rest of the lecture. All right? So that's very nice. Solve an LP, get what you want. All right, a couple other comments, I guess. So multi-way cut, you know, it's natural to study it just to, you know, as a generalization of the very famous ST-min cut problem. It does show up in applications in various guises. So like image segmentation, right? So if you want to model an image as a graph and you want to break it into different regions, that's often solved by modeling it as a multi-way cut problem. Okay, so if you have a belief that there's like 4 regions, then you have the 4 terminals corresponding to the regions, and basically the 4 parts of your multi-way cut correspond to the pixels of your image that you're ascribing to each of those 4 regions. Okay?
Can you give us a sense of what the barriers are here in this problem?
So as far as like how far can you go?
Yeah.
As far as I know, not much is known about that, actually. I was wondering that myself. So unlike the k-median example where the upper and lower bounds are pretty close, I don't know that anyone's thought about it much, so that would be interesting. I mean, so if someone wanted to do maybe a theory project, this paper has a lot of other results too. So you could talk about the other results in this paper and also maybe think about, you know, what would lower bounds be for this multi-way cut example. Yeah, I'm not sure. yeah, it's really, I could imagine 4 being the right answer, or I could imagine it being a smaller number. I'm really not sure. So,
What's the name of the paper again?
I'll put a link to it on the course page, yeah. Yeah. In fact, I think there's already a link on the course page to it. Yeah. Okay, so that's the result I want to cover. Any questions? All right, the proof is going to follow very similar lines. Clearly, something's going to have to be different because we need to make use of our stronger hypothesis. We need to use the stability assumption. We're also going to need a different rounding algorithm. Okay, so the rounding algorithm has to be a little bit more clever. Okay, the randomized algorithm. So that's going to be the main difference. All right. All right. So I need to tell you what the linear program is. And this is a quite nice and natural generalization of the one I already showed you. So again, we have variables saying the extent to which an edge is cut. So we're again going to have these d values. The semantics are going to be slightly different. So this is going to be for all vertices and for all I equal 1 up to k. So for a vertex v, div is meant to say the extent to which this vertex has been assigned to the ith group. So in an integer solution, right, we're going to have this k-way cut, so we're going to have these k groups. So for a given vertex, we're envisioning all of its d values being 0, except exactly 1 will equal to 1. If it's in the ith group, then its div values equal to 1. Its djv values are equal to 0 for j not equal to I. Okay? That's what we have in mind for these d values. So if you like, this is sort of like a unary encoding of which group you got assigned to. Okay? All right. Good. So constraints. Well, so I guess first of all, the objective is the same as before. That's easy enough. Okay, XE is whether the edge got cut or not, and we pick up the cost CE each time an edge is cut. So how about the constraints? The constraints are sort of interesting. So first, what's clear is that, remember, the ith terminal better be in the ith group. Okay, so in the same way we had S tethered and T tethered, now we're going to have all the terminals tethered. So for all I, Ti better be assigned to the ith group fully. Okay. Also, it better be the case that every vertex belongs to a group, at least fractionally. So if you sum over all of the groups you could be assigned to, that should equal 1. Okay? So again, in our dreams, for a given vertex v, exactly 1 d value is 1 and the rest are 0. Okay? So that's just indicating which group it's a part of. For a linear program, we need these linear constraints. We need real valued variables. So this is sort of the best we can do. We're just going to say the sum of the extents to which you're assigned the group should be 100%. Okay? Good. And so now we need an analog. So before we had these constraints would say that the extent to which an edge is cut is at least the difference in its d values on opposite sides. Right? So xe was at least du minus dv, and xe was at least dv minus dvu. So we need analogs of that. And so these are slightly more complicated. So we look coordinate by coordinate. And we have a notion of sort of how far two vertices are apart in a given coordinate, and then we sum up over the coordinates. Okay, so ye should be at least, so this is for an edge E with endpoints uv. Yeah, so we have 2 of these. And with these flipped. Okay, so again, this is just, we have 2 constraints just basically saying this y value should be at least the absolute value. Okay, I write it this way so it's obvious it's linear. And then at the end of the day, finally, we say the extent to which we call an edge cut is just the sum of these y values, the extent to which they're cut across each of the coordinates. Actually, I need to change this. I need to do something slightly different. Okay? But this is basically it. So how should you think about this? Okay. Well, again, remember, whenever you're trying to interpret the linear relaxation, think about, okay, what are the intended semantics for an integer solution? Okay. Always anchor that in trying to parse these things. So the intended semantics would be, okay, well, suppose you have a vertex that's in group 7 and another vertex which is in group 10. That means the edge between them got cut for sure, right? So we want the fact that they're in different groups to force us to set xc to be equal to 1. Okay, that's what we're trying to accomplish, all right? So what does it mean that a vertex is in group 7? It means that all of the d values are 0, except it has a 1 in the 7th coordinate, and then its mate has a 1 in the 10th coordinate and zeros everywhere else, okay? So that means that there will be exactly 2 coordinates when I equals 7, when I equals 10, so that this difference is 1, or the max of these differences is 1, okay? So that means when I sum this up, I get 2, actually. And so something's a little off. But here's a quick fix to that. Just do a half.
Why don't we just say that xc is greater than all yu's?
Well, so that would be weaker. We could. That would be legitimate. But if you think about it, this is sort of a stronger constraint once you're dealing with fractions. Right, so the sum is bigger than the max. Right, so basically we want to force the linear program to keep the x's high. Okay, so the bigger legitimate lower bound we can write down on the x's, the stronger we expect the linear programming relaxation to be. In the sense, the smaller the gap we expect between whatever the LP solution is and the integer solution. But you're right that if you only focus on 0, 1 variables, then you may as well do max instead. Okay. All right. So again, why 1/2? All this stuff. It's because in the canonical case where these are 0s and 1s, this sum is going to be equal to 2. Exactly the 2. You get contribution of 1 from each of the 2 groups that the endpoints are present in. You cut it in half, so you get 1. Okay. All right. So that's good. So this says whenever you're assigned to different groups, you're forced to be cut. And similarly, if you're at least sort of fractionally assigned to sort of different groups, it's again going to force the edge between you to sort of be cut. Okay? So you're going to pay for the edge on some sort of prorated basis based on how different the labelings of your endpoints look like. Okay? All right, so that is the linear program. Any questions about that? I mean, another way you can sort of think of this, which is maybe useful geometrically, is you can imagine that in this linear program, instead of assigning, so in the integer problem, in the discrete problem, you want to assign each vertex to one of the 3 groups. Okay? Think of the 3 groups as corners of a simplex, of a triangle. Okay? And so basically what's going on is, in the linear program, we can't get away with forcing each vertex to be assigned to one of the corners of the simplex. We allow the linear program to assign a vertex anywhere inside the simplex. Okay? So that's sort of a way to interpret its labeling. Right? So when k equals 3, a given vertex gets 3 values, 3 dv of 1, 2, and 3. You can think of those as being a coordination of the simplex. All right? So that's a geometric way to think about what it's doing. All right? The real problem is, I give you a graph, you want to assign the number 1, 2, 3 to each of the vertices. What can you do in polynomial time? You can assign a point in the simplex to each vertex. Okay? And then what this is all saying, this is saying that you're going to pay, so when you assign vertices to points in the simplex, the further apart they are in the simplex, the bigger fraction of this edge you're going to pay for cutting. Okay? And this is some kind of basically L1 norm of where you put the 2 endpoints in the simplex. That's another way to think about it. Okay? Questions?
So in that sense, we probably still have a guarantee that there is an integral optimal solution. We just can't necessarily select it with an LP solver.
No, so right. So the facts still hold. So we can still solve this linear program in polynomial time. So without assumptions, it's not going to solve to an integer solution. And actually, on the homework, I'm going to ask you to just to get a better feel for this, look at a concrete instance where the LP actually does strictly better than the best integer solution. But in some sense, we know this morally, automatically, because this is an NP-hard problem, and we can solve the LP in polynomial time. Right? So we just know it's going to be wrong sometimes. And here, for a linear program, what wrong means is it does too well, right? So it actually, right, it's going to do at least as well as the best multi-way cut, but it has the potential to do even better, but by making use of these fractional solutions that we have no immediate use for. Okay? So the magic here is we're going to say, okay, in the worst case, certainly the LP will be strictly better. Okay, it'll have a truly fractional optimal solution under a, somewhat reasonable stability condition. The gap goes away, guaranteed. Okay, that's the magic here. So really, so the way you should think of it is, this theorem is really the exception that proves the rule. Okay, so when you're talking about, most problems that we care about, outside of a few, just very happy positive results like, bipartite matching, max flow, et cetera, linear programs generally are not guaranteed to do what you want. And so this is great. So we can actually guarantee that you just solve them and don't have to do anything else. It's a very happy day. So. Okay. All right. So on to the proof. Any questions? Okay. All right. So there'll be a part of the proof which mirrors fairly closely what we already did for minimum cut. So I'll go through that, but I won't belabor it unless there are questions, because it should be the second time you're seeing it. And then again, what we have to do differently is the rounding algorithm. Okay, so we're going to have to do something smarter than that idea where we just blew up a balloon with a random radius. All right? That's also the algorithmic piece, so my guess is you'll find it the most sort of clever and intriguing. All right, but so proof. All right, so notation, so it's going to be the same gist, but we somehow have to make use of this stronger assumption that it's 4 stable, okay, or better than 4 stable. So here's what I'm actually going to do, is motivated by the fact that we're assuming 4 stability. Remember what that means, okay? That means even if we perturb things by a factor 4, this opt stays opt. It's still better than everything else, okay? Now actually, here's sort of a simplifying intuition you can keep in mind. The stability condition's kind of a little hard to get a feel for initially because it talks about all perturbations, right? But actually, if you think about it, if you think about like cuts, say like a 3-way cut, there's very strong intuition for so suppose you wanted to prove that this wasn't 4 stable, okay? So suppose this is the original optimal solution, and I wanted to exhibit a perturbation to convince you that this wasn't 4 stable. There's actually, it seems actually kind of intuitive which perturbation you'd probably use, or the first one you'd try, right? So remember, what you're allowed to do with perturbation is you're allowed to blow up costs. And remember, the objective function is to minimize the costs of cut edges. So the really kind of adversarial thing you do would be, all right, well, if this is your optimal solution now, I'm just going to look at the edges that you're currently cutting, and I'm going to blow all of those up by a factor of gamma, by the most possible, okay? So I'm going to hurt you as much as I can, and meanwhile, I'm going to leave everything else exactly the same, because this wouldn't hurt you and would hurt your competitors, okay? So in some sense, actually, there's a strong intuition that, and there'll be a homework exercise about this, which is the perturbation you should think of as just blowing up the cut edges in opt by gamma. And that's sort of the relevant perturbation, okay? So that's going to motivate how I define this. So basically what I'm going to do, so it used to be that we had that, so our old assumption was just that there was a unique opt. So now not only is there a unique opt, but it's still opt even if we blow up all of the costs of its cut edges by a factor 4, okay? So I'm just going to write that down. It's going to be the same expression as we had before, except with an extra 4 in it, reflecting this kind of worst case perturbation, okay? All right, so first, I don't expect you to remember the exact details, but this is what it was. So again, this is supposed to say how much, so this used to be how much worse is C than C star. Now it's how much worse is C than C star after we blow up C star's cut edges by a factor 4. So for the stuff that C star does not cut, we don't blow it up, so there's no 4 here. And this picks up an extra CE whenever C cuts an edge that the opt did not. Okay, so that's extra cost for C. And then over here we have this 4. Okay? So this is summing over edges that opt did cut, F star. These are the ones that we blew up by a factor of gamma bigger than 4. So I'll just use 4 here. And if E is not cut by C. Okay? So this is exactly what we had before, except there's this coefficient of 4 in the second term. Otherwise, it's exactly the same. All right? All right, so homework, just making precise the intuition we just said, which is that by gamma stability, actually this is pretty much immediate, but I think it's good for you to just make sure you're solid on it offline. So for every cut, let's see, so for C star, this is 0, because again, both sums are vacuous when C equals C star. And for anything else, it's strictly positive by gamma stability. Okay? Because C star beats C even after you've blown up the cost of all the edges in F star. Okay. So that's one thing, and this is sort of where we're encoding the stability constraint. The next thing we did is we said we wanted to do something similar for the LP solution. Okay? And for the LP solution, we're not going to have the 4. Okay? So the LP solution is just the same statement as before. And the definition is actually exactly the same. Okay? And again, because the LP solution is at least as good as the best multi-way cut, the multi-way cut is one feasible solution for that linear program. The optimal solution can only be better. This, again, for exactly the same reasoning, is non-positive. Okay? So delta of x hat is just saying how much better for the LP objective function value is the fractional optimal than the cut C star. And that's non-positive. Okay? All right, so now here's going to be the new lemma. And remember, the lemma is what talks about an algorithm, a randomized algorithm. Okay? So what did our old lemma say? Our old lemma for just the min cut problem said, look, I'm going to output a random ST cut, okay, so a distribution over cuts, so that the probability of an edge getting cut is exactly what the LP says it should be. Okay, that was our old lemma. Okay, every edge was cut with exactly the probability that the LP wanted it to be cut with. We're not going to be able to prove that now. Okay? Because if we could prove that lemma, then we'd get a polytime recoverability result without the stability constraint. Okay, so that's too strong. It's an NP-hard problem. Okay, so we don't expect that exact same lemma to be true. We're hoping that that lemma, relaxed in modest ways, is true. Okay, and it is. That's the case. All right. So what's true is there exists a randomized algorithm that outputs, with probability 1, a feasible cut, multi-way cut C. And, right, so such that for all edges, two things are true. So what did we say? What was our old lemma? Okay, the probability that you cut the edge is exactly x hat e, and therefore the probability that you don't cut an edge is exactly 1 minus x hat e. So we're just going to have versions of both of those statements that are off by a factor 2. Okay? So the probability that C cuts E, before this equaled x hat E, the new statement is it will be bounded above by 2 times x hat E. So it might be more, but only twice as big. And secondly, okay, so notice what this would imply is just that the probability that is not cut is lower bounded by 1 minus 2 times x hat E. Okay, it turns out that that's not going to be good enough for the analysis we're about to do. So we want a better lower bound on the probability that it's not cut. So the probability that E is not cut, so before this equaled 1 minus x hat E, and now we're going to argue that it's at least that same factor divided by 2. That's a 2 on the bottom. Okay? So notice that does not follow from 1. Okay? What follows from 1 is a lower bound of 1 minus 2 x hat E. Okay? This is a different lower bound. Okay? So let me again show you why, given the lemma, we're done. So why does the lemma imply the theorem? So it has exactly the same, it's exactly the same as before, basically. But let me show you the calculations. So basically the 4 is going to cancel out these two factors of 2 that we lose, okay? So let's compute the expected extent to which the multi-way cut output by the randomized algorithm is better than the optimal one after we've blown up the costs of f star by a factor 4. So again, just by linearity of expectation, we can just analyze that term by term. So sum over the edges not cut, CE, times probability that C cuts E, minus sum over the edges that C star does cut, CE times the probability that E is not cut by our random multi-way cut. Okay, oops, there's a 4 there, sorry. Forgot the 4, which is an important 4. All right, so again, that's just linearity of expectations. Applying the lemma part 1, this is the most 2 x hat E, right? Applying the lemma part 2. Right, so we're shooting for an upper bound here, just to be clear, all right? So for the positive term, we want an upper bound. For the negative term, we want a lower bound, okay? So we're subtracting something smaller, so overall, it's bigger, okay? So this, we have a lower bound of 1 minus x hat E quantity over 2, okay? By lemma part 2, all right? That's just plugging in the lemma. And so what do we have? So we pick up a 2 in front on this first term. We pick up a 1/2 here, which cancels one of those. So down here we get a minus 2, sum over E in F star, CE 1 minus x hat E. Also known as 2 times delta of x hat. Last I checked, double a non-positive number was still a non-positive number. So the expected extent to which the random output C is better than C star is non-positive, okay? But again, every single output, okay, is, is strictly worse than C star unless it's actually C star. So the only way this can happen is if with probability 1, this randomized algorithm outputs the stable optimal multi-way cut C star. And again, once I show you the randomized algorithm, it will be clear that the only way it's going to have a constant output is if you fed it in an integer solution in the first place. Okay? So it means that the optimal LP solution x hat had to have been integral. Okay? So questions about that? Yeah, so in some sense, where does the stability condition rescue us? It allows us to absorb the fact that we can't perfectly mimic the LP in some distribution over multi-way cuts. We lose a factor 2 in upper bounding the cut probability, a factor 2 in lower bounding the uncut probability, and the stability factor of 4 kind of absorbs both of those. Okay. All right, so what is this randomized algorithm? So this is again very simple, but this probably isn't the first one you'd think of or first one you'd try. Whereas the balloon growing one, I think for some people it's maybe the first one that they try. Okay. So I'm going to tell you what it is and leave the analysis to the homework. So algorithm for the lemma. And so again, we're given the x hats, which we'll ignore actually, and the d hats. Okay, so remember every vertex is assigned to a point in the simplex. Okay, So it has 3 coordinates, if you like, the extent to which it belongs in the ith group for each value of I, 1 up to k. Okay, so that's sort of the input to the rounding algorithm, to the randomized algorithm. Okay, now, here's the randomized algorithm. So initially, all vertices are unassigned. If you wanted, you could seed it by assigning the terminals to the appropriate groups, but it actually doesn't matter. Okay, so just think of all the vertices as assigned. So here's what you do. Okay, you're going to do a loop until everybody's assigned. And in each iteration, you're going to do a random experiment, which may or may not assign some of the vertices to some of the groups. Okay. In each iteration of this loop, you're going to make 2 independent random choices. Okay? One choice will be a threshold, very much like our random radius for the minimum cut case, the ST cut case. The other one will be a random group, which is who you're going to assign labels to in this particular iteration. Okay? So you choose a group between 1 and k, uniformly at random. And you choose a threshold, R, again, uniformly at random. Okay? And then you look at all the vertices which have not yet been assigned to a group. Okay, now let's just remember this, right? So suppose I have a vertex V, and I'm looking at like group number 7. So I'm looking at like D sub V superscript 7. Right? So remember the semantics. The bigger that number is, the greater extent to which we fractionally assigned it to the 7th group. Okay, so the higher that D value, the more the LP is suggesting it should belong to the 7th group. Okay? And we want, you look at our desiderata for this rounding algorithm, it means also that, the probability that we wind up assigning this vertex to the 7th group also better be going up, okay, with its D value. All right? So that suggests saying, the higher its D value in this coordinate, the more likely it should be that it gets assigned to this group. So let's just use this R as a threshold and just say, as long as you beat the threshold, meaning you're above it, you get to go to this group. Okay? So V unassigned, and the extent to which V is assigned by the linear program to group I is at least R. Then assign V to the ith group. Okay? So that's the algorithm. So it's definitely going to output a multi-way cut. Remember that the terminals are fixed to have these kind of basis vector coordinates. Right? So the terminals are 1 in the ith coordinate, 0 everywhere else. That means the only group they can be assigned to is the one they're supposed to, the ith group. Okay? It's not obvious that it satisfies these 2 properties, but it does. Okay? It's not that hard to prove. Okay? So that's why I want you to think through it. Just to make sure it sort of makes sense. So imagine you have an edge, UV, and say in this linear programming, this alleged fractional solution, the coordinates look like 1/2, 1/2, 0. Let's say k equals 3, and 1/3, 1/3, 1/3. Okay? And just sort of, this is a randomized algorithm, so a lot of different stuff can happen. Okay? So just before we adjourn, I just want to mention a little bit of intuition about what can happen, right? So we're interested in whether or not this edge gets cut or not. Okay? And this is saying we want to have like pretty good control on the probability that it gets cut from either side. Okay? And basically it gets cut, right? So if one of these gets a certain label and the other one doesn't. All right? So for example, if the random choice of I equals 3, then you're like, okay. Well, if we choose the 3rd coordinate, okay, then there's no way U is going to be assigned to group 3, right? Because its value is 0. There's a 1 in 3 chance that V gets assigned to group 3, okay? And so if that actually happens, if we wind up picking R, the threshold, to be below a 3rd, then indeed V gets assigned to group 3, and we're sure that this edge is going to get cut. Okay, definitely. Right? So whenever coordinate 3 is chosen, either neither vertex gets assigned, or the second one is assigned to a group that the first one will never be assigned to. On the other hand, maybe we choose R equal to 1/2. Okay? And then V doesn't pass the test. Okay? And then this edge lives to survive another day. okay? And now maybe on the next day, we re-choose I, maybe we choose I equal 1, okay? So now a couple different things can happen. Right, so now we have 1/2 and 1/3. One thing that could happen is we choose R strictly below 1/3, okay? And then in one fell swoop, both U and V are going to be put in group 1, okay? So there's no way this edge is going to get cut. It's safe forevermore, because you only get labeled once. On the other hand, we might choose R strictly between 1/3 and 1/2, okay? And then that's pretty dangerous, right? So that says that says U gets labeled 1, V doesn't get labeled, so maybe we'll get lucky, it'll get labeled 1 later, but that's sort of a, unlikely chance. It could happen, but you wouldn't want to count on it. On the other hand, maybe you choose R to be strictly bigger than 1/2, neither one gets labeled, and we just start the process all over again, okay? So there's these different ways that things can get resolved for this edge. It turns out, if you think about it, a few lines of probability prove that actually the cutting probability and uncutting probability are both tightly controlled around what the linear program wants them to be, okay? And so the fact that you lose only a factor 2 in either one is what gives you the force stability result. One final comment about why this is cool. So there's this big cottage industry of linear programming rounding algorithms, okay? So you have an NP-hard problem, and the traditional approach, which is also useful in practice often, is you solve a linear relaxation. It has some fractions. And then you do something maybe stupid or maybe clever to round the fractions into integers. And hopefully you don't lose too much, okay? So maybe you had a fractional solution, you round some things, you get something which is 10% more expensive, but now it's an integer solution, okay? So there's lots of algorithms which kind of use roundings to transform fractional solutions into integer ones. A key ingredient of these theorems were these rounding algorithms, okay? But notice, they're not our algorithm, right? Our algorithm is solve the LP and declare victory, okay? So these rounding algorithms, which again, people have been developing machinery, for understanding these rounding algorithms for decades, we're actually now just using them in the proofs to explain why LPs solve exactly in stable instances, which is a, pretty neat thing. All right, so I won't be here Monday, but I'll see you for a doubleheader a week from today. Have a good weekend.